Hello, welcome to Noise Control and its Management. Today is the fourth day of this particular week, and starting today we will discuss about enclosures and partitions as to how these types of approaches can be used to reduce noise. So, what we will discuss today is noise in an adjacent room or noise from an adjacent room. So, here is the context. Suppose I have a room, it is a big room, and there is some machine which is producing noise, and there is a person here, and we are measuring sound power level or sound pressure level at this location, and suppose this sound pressure level is very high. So, we want to reduce noise, and of course, noise is coming because of vibroacoustic as well as airborne mechanisms. So, one way to reduce this noise is I create a wall here. So, now I have instead of one room, two rooms. So, the question is that once I have a wall, so once I have noise coming from this room and I have a wall, I am interested in finding out that how much the value of LP is once I introduce a wall and I make this into a partitioned room. So, that is why the title is noise from adjacent room, that there is a source, there is a wall and there is another room, there is a wall which separates these two rooms. How much noise is coming in this room? This is the problem. So, let us say this machine produces some watts of sound power, and associated with that power the sound power level is LW. Now, these are two rooms. So, this is room number 1, this is room number 2, and each of these rooms has a room constant. So, this is room constant 1 and room constant 2. If you remember the definition of room constant earlier, we had given that room constant for any room is what? The total of internal surface area of the room times average absorption coefficient of the room and plus 4 mV divided by S naught, where m is the energy absorption coefficient attenuation constant due to air divided by 1 minus alpha bar minus 4 mV by S naught. Okay. So, V is volume, S naught is this thing, internal surface area of the room, alpha bar is the mean average surface absorption coefficient of the room. So, the question is, given LW, what is LP? This is what we are trying to figure out. So, the answer to this question comes from a lot of mathematics and also based on analytical formulations as well as statistics as well as some empirical data, and what I am going to write down is directly the result. Okay. So, in this room I will call the sound pressure level LP2, and suppose this is a point in this room. So, this is LP1, and the distance between the machine and the point here is R1, and the distance from the wall. So, in this case the distance from the wall to this thing is R2. So, with this context, here is the, I will directly give the result and then we will learn how to use it, because that is more important thing about this course. So, LP2, which is the sound pressure level at any point in room 2, is equal to LW minus 10 log 10 of room constant R1 plus 10 log 10 of 4 SW, and I will explain that, divided by room constant R2 plus 1 if R2 is less than SW by 2 pi, and this is LP2 equals LW minus 10 log 10 of R1 plus 10 log 10 of 4 SW by R2 plus SW by 2 pi R2 square. Oh, I am sorry, this is, I missed some terms here, minus TL plus 0.1 if R2 is less than SW divided by 2 pi, and this is again minus TL plus 0.1 if R is more than SW divided by 2 pi, and I will explain what all this thing means. So, SW is the surface area of the wall, it is the surface area of the wall. TL is transmission loss across wall. And this is R2. Okay. So, let us look at these relations and try to get a physical understanding of it. R1 and R2 are room constants, and look at the room constant. The room constant will increase if alpha bar goes up. Okay. What does that mean? It will increase if alpha bar goes up or if S naught goes up. If alpha bar goes up, what will happen to the factor in the to the numerator? It will go up. What will happen to the denominator? It goes down. So, R will increase as alpha bar goes up, which means if I have more sound absorbing materials in the room, then R will, the room constant will increase. Similarly, if the internal surface area of the room is large, then room constant will increase. In context of noise level at this point P, what do you think? If there is more surface area in the room, what will happen? More sound energy will get absorbed, which means the sound pressure level at this point P will be lesser, and that is what this relation also tells us, that as R increases, R1 increases, sound pressure level goes down. Similarly, as R2 increases, R2 is in the denominator, sound pressure level again goes down. Okay. So, sound pressure level can be reduced if I can increase my room constants R1 and R2, and the room constants can be increased in two ways, either by increasing the surface area of the room or by having better sound absorbing materials in the room. So, this is one thing about this relation. The second thing is TL, transmission loss. So, what is transmission loss? Suppose, so I will explain that. What is transmission loss? Suppose I have a wall and here it is 100 decibels Suppose there was no wall, suppose there was no wall and here it was 100 decibels and at this point it was 98 decibels. In absence of wall, then as sound travels from here to here, it falls by 2 decibels, right. Suppose I introduce a wall and then all of a sudden it becomes 68, which means that the wall is causing a loss of transmission of how much? 30 decibels of sound. So, the decrease in power on the logarithmic scale which gets transmitted across the wall is known as transmission loss. Okay. Now, how do you get this transmission loss? It depends on the material properties of the wall, it also depends on how thick the wall is. So, there is no hard and fast formula right now, we will talk about right now. But if we know the transmission loss of the walls, and sometimes you can actually buy some of these partitions from the market and they will specify what is the transmission loss of those partitions. So, either you calculate the transmission loss using finite element analysis or things like that, or if you are buying a purchase product, they will actually specify what is the transmission loss. So, transmission loss, if transmission loss is known, then you can calculate the sound pressure level in the adjacent room using these two relations. If the value of R2 is more than this ratio SW divided by 2 pi, the whole thing under square root, then you use the second relation, otherwise you use the first relation. Okay. So, this relation helps us calculate what is the sound pressure level in an adjacent room if there is a machine which is creating a lot of noise. So, let us look at an example. So, consider a large room which has a partition. Okay. So, this is room number 1, this is room number 2. Actually, before we do this, I would like to specify one more relation, because what I have said was that what we will discuss is, we will discuss how to compute LP2 and also how to compute LP1. Okay. So, to compute LP1, we have another relation LP1 equals LW, and this is something which we have explained in one of our earlier classes also, plus 10 log 10 for closed rooms 4 over R1 plus directivity factor Q divided by 4 pi R1 square plus 0.1. So, now we go back to our problem which we were just starting to define. So, suppose there is a machine here M and there is a person operator. So, this is the room. So, this is an operator room and this is the machine room. Okay. This is an operator room and there is a machine room, and the machine generates a lot of noise. So, we want to make sure that the operator which is controlling this machine electrically and through electronics and instrumentation, this person is not exposed to a lot of sound pressure. So, we are interested in finding out what is pressure level in this room and the distance. So, this guy is R2 is this distance. So, R2, so he is about 1.5 meters away from the wall. Okay. The other thing we know is that this wall is having a surface area of SW is 16 square meters. 16 square meters, and then we look at different rooms. So, first we will look at the machine room, and we will look at data in the machine room. So, this machine is generating power, and this is acoustic power, and it is generating 0.033 watts. Remember, this is a small amount of energy, but because we have to, if we have to compute it in decibels, we divide this by the reference power level, which is 10 to the power of minus 12. So, the decibel level becomes very large. So, do not just ignore this 0.033 watts. Okay. So, this machine is generating 0.033 watts. Its directivity factor Q is 2. The area, internal area of the room is S1, and that is equal to 900 square meters. The average absorption coefficient in the first room is 0.05, and the distance of the machine from this point of interest. So, this is P1. So, this is R1 is 4 meters. Okay. And then we look at operator room. So, what are the details of the operator room? So, internal surface area of the room is 100 square meters. The surface absorption coefficient on an average for the entire room, alpha 2 bar, and we know how to compute it. So, I am just giving you directly the value of it is 0.35. The area of the wall SW is 16 square meters, and the distance, I will just rewrite that, is 1.5 meters, and the transmission loss is 30 decibels. So, how do we get this transmission loss? Either we use FEA or we use data from suppliers to compute this transmission loss. So, given this information, the question is, calculate we have to calculate LP2 and LP1, and the second thing we have to do is so this is what we have to calculate. And if we think that the pressure in the second room is very high, sound pressure level, then how do we further reduce this sound pressure level in the second room? So, this is the problem. To do all these calculations, let us look at these relations. We have to know LW, we have to know R1, we have to know R2, we already know transmission loss, right, but we have to compute these LW, R1 and R2 before we can say something concrete about sound pressure level in the rooms. So, LW equals 10 log of 10 power level, and how much is power? 0.033 divided by reference power 10 to the power of minus 12, and if you do all the math, this comes to be 105 decibels. Okay. So, the sound power level attributable to this machine is 105 decibels. Next we compute R1. So, what is R1? R1 is S naught times alpha bar plus 4 mv divided by S naught divided by S, excuse me, 1 minus alpha bar minus 4 mv by S naught, and this is for room 1. So, I am going to specify these things. Now, here we have seen couple of earlier times also that this is not a very large room, right. So, the role of air is not significant, air does not absorb a lot of sound, it does not absorb a lot of sound. So, we can ignore the contribution of air. So, that is why, so we will not bother about it, but if we want to be more accurate we can include the contribution of air, but then we have to know the value of m, and then once we know that, then, and of course, we also have to know the value of v. So, we can, so that is there. So, with that thing in mind, we compute this thing. So, S naught is how much? 900 square meters times alpha 1. What is alpha 1? 0.05. This is the surface absorption coefficient of the first room divided by 1 minus 0.05. So, this comes out to be 47.37 meters square, and then R2 equals S2 times alpha 2 divided by 1 minus alpha 2. So, once again, when I am computing the room constant for the second room, there also I am ignoring the contribution of air. So, that is equal to 100 times 0.35 divided by 1 minus 0.35, and that is equal to 53.85. Okay. So, remember, just it is important to understand something here. The room constant for the first room is 47 and for the second one is 53. If you look at the size of the room, the first room, its internal surface area is 9 times more. You look at this number, 900 is 9 times more than that of the second room, but still the room constant for the second room is slightly more than that, because the surface absorption coefficient of the second room is 0.35 compared to 0.35, and because it comes in the denominator, as this number becomes larger and larger and becomes closer to 1, this room constant value goes up very rapidly, very high. So, if you can increase alpha rather than work on increasing surface area, you will get much better benefits. Okay? So, this is important to understand. So, I think now what we have done is we have set up our problem correctly, and we will continue these calculations also in the next class and finish this, and then try to learn something from this example which will help us understand how can we design effective enclosures in situations like this, where we have a large room with a separation of a wall, and we want to make sure that the sound coming from the adjacent room where we may have a machine or something is as less as possible in the room where people are staying. So, that concludes our discussion, and I look forward to seeing you tomorrow. Thank you.